So far, when we've talked about hypothesis tests and making optimal properties or defining optimal properties, we've really stuck to simple versus simple. But what happens when we have a situation that is not simple versus simple and we have composite hypotheses? Can we still find optimal properties? And that's really what section 9.3 is about. It's not about all possible hypotheses beyond simple versus simple. It's really just about one-sided tests, the two types of structures that we have here at the top. So that's what we're focusing on in section 9.3, just these structured hypotheses and what optimal properties can we still find. Now, before we dive too far into optimal properties, we need to introduce a new concept called a uniformly most powerful test. In this definition of a uniformly most powerful test, it is dependent on, or it's structured around, this power function. Now, if we remember, a power function is the probability we reject H naught given some theta. So just to recall what power functions look like, I'm going to use this one as an example. So this is the one we're going to be thinking about for now. And a typical power function we might see for this one. So let's say we have a level alpha test, or that is our goal, is to have a test that has level alpha, or a level alpha naught. A typical power function we might see has a power curve that is below this goal until some point, and then it starts going up. So I'm thinking normal distribution situation would have a power curve that might look like this. And I'm going to call this test delta 1. So the first type of test we're thinking about, and this test would have this corresponding power curve. Typically, the point where it crosses the threshold, or crosses alpha naught, where we're trying to keep our type 1 error rate, typically at that point is where we are at for theta naught, the upper boundary of the null parameter space over here. That's typically where we cross theta naught, alpha naught, so where those intersect. Now, there's lots of tests that we can consider for every possible situation. For instance, maybe one that's a little bit silly is, suppose alpha naught is 0.05, so about 5% chance. Let's say I get a 20-sided die, and it doesn't matter what data I have, doesn't matter what the true parameter is. I roll this die, and if I roll 1, I'm going to reject my null hypothesis. If I roll anything else, I'm going to fail to reject. So it doesn't matter anything about data or my parameter. I always have a alpha naught, or a 5% chance of rejecting my null hypothesis, no matter what. So we can consider that as a test. So that's a second power function. It's always at 0.05 that we might consider. Let's consider a third test. Maybe this one is really conservative. It's always under alpha naught, but it does eventually go above alpha naught when we get in the null space, but it never quite gets high as D1. So I'm going to call this delta 3 as a third test, a little bit more conservative of a test. So it's structured kind of similarly, slightly different rejection zone. And let's get a fourth test out there. And this person is very worried about type 1 errors, very worried about type 2 errors. They're not so worried about type 1 errors. So what they're going to say is, you know what, no matter what my data is, I don't care the situation. I'm always just going to reject the null hypothesis because that's how I feel. So at 1, probability of rejecting null hypothesis, this person always rejects. It's kind of a silly test, but they always reject, and I'm going to call this delta 4. So these are 4 possible tests that we might consider for this situation, and they're 4 power curves. Now, for the situation that I boxed, this over here is the null parameter space. So all the values over here are when the null is true. If we reject H naught and our theta naught is in the null space, this is a type 1 error. So this is type 1 error, and we generally want the power function in this region to be as small as possible. But if I am on this side of theta naught, I am in the alternative space. So in this area, I am making a correct decision. I am rejecting h naught and h naught is true. So generally we want the power function to be as large as possible when we are in the alternative space. Now I'm going to talk about this definition in non-technical terms. We're going to let alpha naught be some fixed value. So some fixed value that we're not paying attention to. You can think 0.05 just for simplicity. Among all tests that satisfy their type 1 error rate is below alpha naught, we say a test delta star is UMP, uniformly most powerful, if the power function is largest at all values of theta 1 that are in the alternative space. So this is a non-technical version of the definition that you have, but basically it is saying if we restrict our attention to all the tests that have a type 1 error rate, always below this predetermined threshold alpha naught, let's just restrict our attention to those tests. So that's this first part. If we restrict our attention to just those tests, we immediately rule out delta 4. We're not thinking about these fourth kind of silly tests that we made that always rejects h naught, because our type 1 error rate does pass alpha naught. In fact, it's always above alpha naught. So we're not thinking about that one. We're only thinking about tests in which their type 1 error rate is always below alpha naught for all values in the null space. Then we pay attention over here to the right side of this figure when we're in the alternative space. We say a test is UMP if its power function is the largest out of all possible tests that's under this restriction. So in this case, our UMP test is delta 1 because this is the one that's going to have the highest chance of making the correct decision. And again, this is at every possible value in the alternative space. So this would be UMP. Now, we're living in this world where it's only these 4 possible tests, or at least that's the setting that I gave you. But we can have so many more tests, tons and tons of tests. You can imagine tons of them. We say the test is UMP if it has this property. So it's a really interesting and big, and I want to say powerful property that you can have if this is true. If we have the most power that we could imagine, then we say that that test is UMP.